Okay, so without further ado, let me introduce our first speaker, David Nicewicz. So David had his BS from UNC Charlotte, then went to do his PhD at UNC Chapel Hill with Jeff Johnson. Then went to postdoc with Dave McMillan at Princeton between 2007 and 2009. And I think it's fair to say, really, he was one of the real developers in that group of the idea of photoredox catalysis. So he was a major player in the initial development. And obviously, UNC Chapel Hill liked him when he was a graduate student because he came back to start his academic career in 2009, quickly was promoted through the ranks to full professor in 2018. And he's made tremendous contributions to the field of photoredox catalysis, most particularly bringing in organic photoredox systems that had a much wider electrode potential to really expand the possibilities of the chemistry, and really highlighted some wonderful examples of applying it to CH functionalization. So David, we're delighted to have you here. And I want to say you are the best dressed speaker we have had in all 17 of these symposia so far.
Thanks, Hugh. That was a really kind introduction. These are my work from home clothes, actually. So, you know, when I come into work, I dress down a little bit. It's a real pleasure to be a part of this, and it's a really fantastic center, and I really appreciate the invitation to be a part of this today. It's almost as if Hugh and the center have had some sort of crystal ball and knew that we were going to be doing presentations like this for a while. It's unfortunate, but obviously we'll press on and do the best we can. So I'm excited to tell you today a little bit about the research in my laboratory. As Hugh mentioned, we're involved in the area of organic photoredox catalysis, and I focused on two main projects today that are in my laboratory that involve CH functionalization, two main programs, one in sp3 hybridized functionalization and one in arine CH functionalization. So I'll talk first about our program in sp3 hybridized CH functionalization by talking about this alpha amine CH functionalization program that we have started. So why are we interested in this in the first place? Well, we saw that forming carbon-carbon bonds adjacent to nitrogens on nitrogen-containing heterocycles and acyclic compounds is a valuable disconnection for accessing, for example, bioactive compounds as well as natural products. Just a few examples listed here. And the way we envisioned sort of going about that carbon-carbon bond forming step is through radical chemistry. And obviously, photoredox catalysis is a great way to generate neutral carbon radical species. And so the way that we envision doing that is by starting with some sort of a protected amine scaffold and then generating a carbon-centered radical adjacent to that amine such that it could react with, for example, an alkene to form that new carbon-carbon bond. Practically, how we hope to carry this out is by using a carbamate protected amine. And so how we are listed below oxidation to now access this alpha amino radical species. Now, again, like I mentioned previously, this really was a mechanistic strategy that had been taken advantage of in the past. However, typically this utilized an aryl amines, and doing this with carbamate protected amines is quite a bit more challenging because you need quite a high oxidizing capacity for your catalyst at about 1.9 volts. And I'll talk a little bit about redox potentials in a second. in order to do this one electron oxidation. So that's where this area of organic photoredox catalysis comes into play. And so I often get the question, well, why are you interested in using organic photoredox catalysts? And quite simply, the organic catalysts are much more oxidizing than their organometallic and inorganic counterparts. And so those of you that may be familiar with photoredox catalysis, but may be more familiar with the metal bipyridyl complexes, such as those depicted on the left, these complexes are excellent photoredox catalysts and have fantastically long excited state lifetimes, but they're simply not as oxidizing as these organic counterparts. And to just reference you in terms of some common organic molecules, ultimately, the excited state reduction potential of the catalyst that you use has to be more positive than whatever you're trying to oxidize. So if we orient ourselves in terms of the carbamate protected amine in terms of its redox potential, it's about 1.9 volts. And as we can see, the excited state reduction potentials of these metal bipyridyl complexes are not sufficient enough to be oxidizing, but these organic catalysts are. Why visible light photoredox catalysis? Well, quite simply, we don't want to excite the substrate. Most organic substrates, fortunately, only absorb in the deep UV, whereas these organic catalysts absorb in the visible. And it's advantageous because we can now put all of our light energy into the catalyst and not the substrate. So we've been working with these catalysts for a while. The first was reported by the Fukuzumi lab. This is the mezityl-acridinium catalyst shown here. These absorb blue photons and readily pick up and give up electrons. So they make excellent one electron.
Hey, Dave, I think we're having issues with your audio. I had turned off the video feed to see if that would help, but just so you know, we can't hear you right now.
Yeah, I'm having issues with audio right now. Sorry. Bear with me. Is it connected now?
Yes, we can hear you now.
Okay, I'm sorry about that. Yeah, it seems to be a hardware issue. Hang on. Wait, let's go back here. Sorry. It may go in and out, so just bear with me. I've seen this come up a few times, so I'll try and stop. It usually lasts only a few seconds, so I apologize for that. So we've been working with these acridinium salts for quite some time, and we've also developed multiple derivatives of these in conjunction with sigma. Actually, it should be sigma millipore now. And we find that, for example, you'll see quite a bit from this diterp-butyl mezityl catalyst today that is the most utilized. It's much more robust than the parent Fukuzumi catalyst. And these are some of the catalog numbers for the catalysts that are available through Sigma. Unfortunately, we don't make any royalties off of these, but they're there for use if you're interested. In addition, the Spar lab at the University of Basel, as well as my lab, have reported some much more streamlined syntheses of these catalysts in case you're interested. All right, and so back to the task at hand. With this alpha amine CH functionalization, what we observed is that we could now take just the starting carbamate protected amine, our Michael acceptor, and the catalyst in DCM and just irradiate these with blue LEDs, and we see very good levels of carbon-carbon bond formation in a number of scaffolds, including cyclic, as well as ones that you might see in a lot of pharmaceutical motifs, as well as acyclic scaffolds, albeit on a little bit lower yields. You can really decorate the nitrogen with a variety of different functional groups, as well as having different protecting groups such as CBZ and FMOC. What's really interesting from the standpoint of using this in complex molecule synthesis is that you can use substituted pyridines and get good levels of diastereocontrol in these systems. Additionally, you can see that if we start with a stereogenic center, alpha to the amine on the opposite side of the molecule, we functionalize the opposite side and maintain stereochemical fidelity. Now, in terms of the diastereocontrol, control, we Sorry, I think I'm back again. We wrap first platinum, where this half chair, the transition state is, or ultimately this intermediate, the minimized form is where this is a half chair, and this ultimately positions the methyl group in the pseudo-equatorial position, such that through a chair-like transition state attack of the electrophile or the Michael acceptor occurs to give the diastereomer shown on the left. For the compound on the right, if you recall, having a substitution alpha to a carbamate forces that methyl group in a pseudo-axial position to alleviate A1-3 interactions, and again, approach from the top face via first Plattner type transition state gives the diastereomer that's observed. This is complementary, as some of you may know, to a lot of really beautiful lithiation chemistry from the Beat group. And in fact, this exact substrate has been prepared, albeit they observe the opposite sense of diastereocontrol control. So it's a nice complementary approach there. And then just to give you an idea, we've started to apply this to some natural product syntheses. So we can take this actual first transformation here after deep protection of the Bach group with TFA and then a reductive amination. This now gives a single diastereomer of monomorine 1 enantiopure and is the shortest synthesis of this molecule to date. And that's a simple molecule, this indolizidine alkaloid family, but I think it gives you an idea of where you might be able to deploy this in more complex settings. And that's certainly a topic of focus for my laboratory in the future. With respect to the Michael acceptors, really you can get away with quite a bit here. I would say the main limitation here is as beta-beta disubstituted Michael acceptors don't work particularly well in this. And you can scale this up using a flow setup. This is an actual flow cell, 8 milliliter internal volume. And we simply use a peristaltic pump to pump our reaction solution through that. And we've run photoredox reactions like this on decagram scale, multi-decagram scale without any issues. To give you an idea in terms of how we study mechanism in my laboratory, I'll give you a little insight here in terms of this particular reaction. And so if we look at we can look at the single electron we can look at so if we look at the lifetime of the fluorescence, in the absence of any Bach amine, we see the lifetime here in red. As we add increasing concentrations of the Bach amine, we see that fluorescence lifetime decreases, which is indicative of an electron transfer event. The next step, as I mentioned, is a deprotonation step. And so as I mentioned at the top, ultimately those CH bonds alpha to the amine become acidified, and we were curious as to how much. And so we turned to DFT calculations. And as you see, the starting amine has a pKa of about 30 for those alpha CH protons. And once you remove an electron, removing an electron increases the pKa of those CH protons by 25 orders of magnitude, which is pretty incredible effect, certainly is known in the literature, but I think it's pretty dramatic here. And what we think is that now makes those alpha CH protons acidic enough to deprotonate by a Bach amine. Radical conjugate addition then ensues. And then what we think is the key catalytic turnover step here is that that neutral acridine radical does a 1 electron reduction of that alpha carbonyl radical. This is actually a stable persistent radical. We've studied this by EPR. And so we know concentrations of that buildup in the reaction is often the resting state of the catalyst in these transformations. That ultimately would generate an enolate if it does the reduction. And what we propose is that a proton would be picked up from another molecule of substrate. And so to probe this, we did some deuterium labeling experiments. If we take an alpha deuteroamine, we see that with this Michael acceptor, that deuterium atom is transferred to the enolizable position of the melanonitrile. Just to show you that the solvent doesn't play a role in terms of the final proton or hydrogen atom transfer. If we run this reaction in DCM, that's D2 DCM, we see no incorporation of deuterium in the product. So that gives you an idea in terms of the mechanism and gives you sort of a general overview in terms of one of our approaches to sp3CH functionalization. I want to finish the second half by talking about our program on Aryl CH functionalization. And certainly this is an audience that I don't have to give much of an introduction by, in terms of Aryl CH functionalization. So we're back again. All right, we're back again. I'll give a truncated in that typical base CH sort of directing group that can ultimately ligate a metal to direct metallation to the ortho position of that monosubstituted arene. And then this organometallic species is then intercepted by the electrophile, which is in solution, to ultimately afford an orthoselective process. Now, where we hope to ultimately complement this is by accessing reactive arene cation radical species by 1 electron oxidation of the corresponding arenes. And as you can see from this charge, this DFT calculation, the charge density map on that arene cation radical, the highest degree of positive charge density here is in blue at the para position to that methoxy group. And so it seemed that we might be able to intercept this with nucleophiles, and certainly there were some indications of this in the literature, again, before we even came along, that suggested this might be possible. And so if we have a terminal oxidant in the pot that can do the second oxidation step after loss of proton, this would lead to a para-selective CH functionalization. And so ultimately, this would be complementary to transition metal-based approaches that are generally orthoselective. And then I think importantly, it gets us to new chemical space because we have now nucleophiles instead of electrophiles involved in this transformation. And so I'm not going to spend too much time on this. We published this several years ago now, but ultimately we chose to investigate the use of azoles such as pyrazole, as these are very common in pharmaceuticals. Now using molecular oxygen as the terminal oxidant, we can now form carbon-nitrogen bonds. Again, para to the most electron releasing group. Interestingly, we retain the halides in these molecules, which might be quite a challenge for transition metal based processes due to competing oxidative addition. Heterocycles also work in this context. And then I think from a pharmaceutical standpoint or agrochemical development standpoint, a variety of different azoles work really nicely in this chemistry. And we can do this with much more complex structures that have a lot of different CH bonds that might be susceptible to CH functionalization, and we get good, clean functionalization. And then sterics really aren't as much of a challenge for this reaction as well, which I think is really impressive. Bonds quite nicely. This is the first catalyzation. we can do cyanation, cyanide as our source of cyanide. And then we can use things like primary amines in this case to do CN bond forming reactions. In this case, an amino acid also is reactive in this context. Most recently, we've been able to publish that, for example, diazoalkanes can also accomplish this, which complements a lot of transition metal catalyzed variants in this area. And we've been able to show this on a variety of different arenes and heteroarenes. We've been able to show that other diazoalkanes work in this scope, and that we can do this on pharmaceutical derivatives, albeit the yields are a little bit lower in this case. The last thing I want to show you is that we were ultimately interested in forming carbon-fluorine bonds. And from the standpoint of ultimately introducing fluorine 18 for applications to positron emission tomography. And without going too much in detail into this area, there's been a lot of really nice work from both Tobias Ritter and Veronique Governor's lab in this area. And the prevailing strategy has been to ultimately use, I would say, an organometallic one where ultimately a heteroarene or an arene that's either a halogen or a triflate can undergo an oxidative addition process to generate some sort of aryl organometallic species that is then treated with NF18 source. And just to sort of highlight the challenges here, fluorine 18 is an unstable radioisotope of fluorine that has a half-life of 110 minutes and it decays by positron emission. Ultimately, we'd like methods that utilize fluoride anion, because ultimately this is how the cyclotron generates F18, and typically this is in the form of potassium fluoride F18. I would say that the pre-existing methods in this area offer some opportunities for improvement in terms of avoiding handling unstable organometallic intermediates. And then also an important thing is if this is utilized in a hospital setting, trace removal of transition metals can be problematic. And then a little bit more versatility with respect to synthesis would be ideal. And so for these reasons, we thought we might be able to target a direct CH-F18 bond forming reaction that is catalytic in organometallic. And so in a really nice collaboration with Ariane, such that we BAF as our F18 source. And at least in this first iteration, we had to go to a fiber optic laser setup that allows us now kinetics fast enough for this to be useful. Although we're in development of a flow LED device, my collaborator and I have started a company, LED Radiofluidics, that is actually in the process of developing a plug-and-play device there. But ultimately, we're now able to adapt these conditions, and these are isolated radiochemical yields of pure compound. You might not think 7% radiochemical yield is much to write home about, but for imaging purposes, as I'll show you in a second, that's sufficient. We've been able to introduce F18 label to a variety of different pharmaceutical compounds, as well as the important signaling molecule F18 DOPA. The last chemistry slide I have here is that I'll show you we've been able to develop some novel probe molecules for a variety of different purposes. This first one uses the non-steroidal anti-inflammatory drug phenoprofen. If we introduce an F18 label here, we asked the question, is this a probe that we can use to look at inflammation? You might wonder why this is important. Well, inflammation of the brain is implicated in a lot of diseases such as Alzheimer's and dementia. So if we now look at this control experiment, this is a mouse here, which we've inoculated with the F18 labeled phenoprofen. This is the CT scan. We see nothing different in terms of the mouse here. We see very little by MRI. But if we now induce inflammation in the ear, we see this now with a significant MRI response, indicating this could be a possible way to detect inflammation. And then the last thing is this can be utilized as a method for synthesizing new probes for oncology. And so this is a particular amino acid derivative that we label with an F18 fluorine isotope. And cancerous cells uptake resources faster than healthy cells. And so they uptake carbohydrates and amino acids faster than healthy cells. And so we can use this as a probe to look at different forms of cancer. And as you see here in the orange and purple are two cancer cell lines that are indicated in the mouse that we can now develop probes for. So we have a really powerful method for taking aromatic CH, aromatic Okay, so with that, I'll in terms of organic functionalization. I think you saw all the names involved, a lot of whom are here, former alumni that did some really fantastic work in this area, as well as current students in my lab, Josh McManus and Nick Anuska. I'd like to thank these sources of funding, and again, Hugh, for the invitation today. And I'm happy to answer any questions either now or online or via email.
Okay, great. Normally we get the whole room that I'm in to clap, but here it is only me.
Very good.
So we've actually got a big collection of questions. I'm going to ask a couple of them, but I'd like you, if you can, then go to the question and answers to answer some of them offline. But let me ask you a few of the questions. So this is from Nick Chiappini from Princeton University, who's asking, do you see any improved performance of harder to reduce Michael acceptors on the back end with added hydrogen atom transfer donors?
That's a good question. We don't really see a significant improvement with an added hydrogen atom transfer donor in most cases. I can't say that we've tried harder to reduce ones because that would make the polarity maybe a little bit more mismatched with that. But in terms of the radical addition to that alkene. But that's a good question. I don't know, we've looked at it extensively, but at least with some of the examples we've tried, that didn't seem to help.
Okay, thank you. And this is a question from Nigien Doan, who first of all thanks you for the talk. And given the mechanism you described, that after the radical Michael addition, the radical will abstract the hydrogen from the starting material, does it mean that the reaction is self-catalyzed after the first catalytic cycle? Can we just turn off the light after radiating a while and the reaction still proceeds?
Right, yeah, so good question. Is this essentially a radical chain process? We don't have any evidence that this is a radical chain process. If it is, I would say that the chains are very short, and ultimately you do need constant irradiation. We're not entirely 100% sure of what is doing the final deprotonation step, and if it's a radical based deprotonation or even anionic. So that's some.
Okay, we missed you a little bit at the end of that. David, we didn't quite hear the end of your answer.
Sorry, yeah, it's. Sorry.
Okay, well, Dave, it seems that you've drawn a tremendous interest. You know, normally after you finish a talk, you're supposed to relax, but it's not going to be the case because you've got at least 9 questions online to answer. So we're going to keep you busy for quite some time. So once again, thank you for giving a really exciting presentation. Thank you.
All right. Thanks, you.